I hope I am audible to everyone. Welcome to today's session, Water and Wastewater Treatment. This is ninth week session, and I am Saptarshi Bose here, the PMR Research Scholar from IIT Madras. As usual, we will try to solve few conceptual, theoretical questions as well as few numerical questions. So today's first question is a numerical one. I hope all of you are much familiar with this kind of question. I already discussed during the last session or the few sessions back. If you go and you will find that exactly same type of problems are there. It is related to the disinfection treatment which we do for the water. An effluent at a flow rate of 2,800 meter cube per day from a sewage treatment plant is to be disinfected. The laboratory data of the disinfection studies with chlorine dosage of 18 mg per liter yield the model Nt equals to N naught e to the power minus 0.15, where Nt equals to the number of microbes and surviving at the time t in minutes. And we can also see that N naught equals to the number of microorganisms present initially at t equals to 0. So the volume of disinfection chamber in meter cube you have to calculate, which required to kill 99% of microorganisms, right? So what is the volume of disinfection chamber in meter cube? I'll give some time, maybe 1 or 2 minutes. You can write your answer in the chat section or in call message section. You can type and send. I can check whether it's correct or not. So I'll go for the solution. The correct answer will be 50.71 meter cube, right? Just a minute. So here you can see that the key Q, that was the flow rate, it was 2,800 meter cube per day, and there was M to be the number of microorganisms present initially. We can write it as M, that was M naught, right? This is nothing but M naught, and then 99% of removal of microorganisms. If I go for this 99% removal of microorganisms, that will actually mean that at time t, that 1% of the microorganisms are still surviving, right? If 99% is removed, then 1% is still there, right? That is simply, that's what it means. And here you can see that MO surviving, that is microorganism surviving at time t equals to, we can see that 1 by 100 multiplied by M. Why M? Because this was the initial one, right? So we noted that N naught, this was the initial one. And now how many microorganisms are surviving? Only 1%. So 1 multiplied by M. And if you write that, I think all of you are aware of this expression. This is nothing new to you, right? So we can write in such a way that 1 divided by 100, that is 1% multiplied by M, that is the my at time t. This is this much of microorganisms I am having. That is equals to M multiplied by e to the power minus 0.15 t. That is the model, right? So the t at the t time t, this is my time t. How many microorganisms are present? That is 1%. So it will be 1% of M, right? And that will be equal to how much? N naught. N naught was the initial one. That is will be M multiplied by e to the power minus 0.158. That's what is written here. So if you cancel out mm, you will get what is the t. Just calculate what is the t. Use ln and you will get 26.069 minutes. You can convert into days, 0.018 days, and then we know that v equals to q multiplied by t. So the v equals to, what is the my q? Q is the flow rate, that is 2,800 meter cube per day. So 2,800 multiplied by 0.018 days, and you will get the volume as 50.4 meter, right? So that is my answer. Next one, the conceptual one. The presence of rotavirus in the drinking water can cause severe diarrhea and intestinal distress in the children. If respective species of virus is present in the raw water, then as environmental engineer, which of the following disinfectant or disinfectants would you suggest for its 99% inactivation? So you have to suggest which method or which disinfectant will kill 99% of the rotavirus. So write your answer in the chat section or in call message section so that I can read. Just a minute. So the correct answer is A. I will not wait today much more because we have many questions to solve. So the first answer is the correct one, that is UV, or the better to say the first option is the correct one, that is UV. Then which of the following is not a suitable method to control the formation of disinfection byproducts? One more thing to add, like here, you can see that chlorination will not completely remove this rotavirus. Ozonation is also not helpful, but if we can directly change their RNA structure, it can destroy it and eventually it will degrade. In case of ozonation, it can degrade only the outer surface. Maybe some of them will be present depending upon the dosage and the kinetics, but in case of UV, it can be completely destroyed or the inactivation will be around 99%. So here it is, which is not a suitable method to control the formation of disinfection byproducts. All of you are aware about these disinfection byproducts. Whatever organic materials are present in the water that will react with chlorine and it will form some byproducts which are carcinogenic. Mostly they are carcinogenic. They will cause cancer. So the correct answer is D. That is the sand filtration is not suitable. In case of membrane filtration, we can remove all the disinfection byproducts. Enhanced softening and enhanced coagulation will also help. The next one is the breakpoint chlorination is required to ensure free chlorine residual for better disinfection. That is the assertion, and the reason is written as free chlorine residuals have good disinfecting power and they are usually dissipated quickly in the distribution system. So you have to write mark the following correct answer: A, B, option A, B, C, or D. Okay, and Nicholas, thank you for quick answering. You are saying option C. Okay. But unfortunately, the correct answer is B. Both A and R are true. Both are true. That breakpoint coordination is required. So all of you are aware about this. Coordination is required. This is my breakpoint to ensure the free coordination residual for the better disinfection. So there will be some residual in the water as free chlorine, and then the next one is free chlorine residual have good disinfecting power, right? That's true, but they are usually dissipated quickly in the distribution system. That is also true, but this is not the reason, right? This is not the reason. That's why we have to use it. So that's why we can say okay. So the next one is the rapid sand filter consists of carefully sieved sand at the top of the bed of the gravel, which will only filter the particles larger than its pore size. That is statement 1. And the next statement is, in addition to straining, adsorption, continued flocculation, and sedimentation in the pore spaces will help in particle removal. Right? Okay, the correct answer is B. That is the statement one is false because in case of rapid sand filter, we don't use the bigger cables at the top. We use bigger cables at the bottom, right? So the statement one is false, and statement two is right because in addition of straining, this is straining at the top layer. In addition of only straining, the adsorption can happen on the sand particles, the pores on of the sand particles, the surface. Then continued flocculation can happen because this will provide some spaces where the flocculation can happen, and the sedimentation at the end, it will sediment on the surface of these sands that will help the particle removal. Yes, that is true. So the next one is the filters differ in respect of standards regarding non-uniformity of the sand used in their filtering media. The two sand filters do not differ in the respect of effective size of the sand particles used in them. The two filters differ in respect of their rate of filtration. So the correct answer is, okay, I got answer from Nikhilesh. That is the B. You are saying B. The two sand filters do not differ in respect of effective size of the sand. But unfortunately, the correct answer is A. They will differ. So this is the wrong one. So answer first of statements, third statements are first statement and the third statements are the correct statements because the filters differ in respect of standards regarding non-uniformity of stands used in their filtering media. Right? So depending upon uniformity or non-uniformity, they will differ. In case of rapid sand filter, you can see that uniformity, but in case of slow sand filter, you will find that non-uniformity much. and that the two filters differ in respect of rate of filtration. Yes, that's very simple, right? In case of slow sand filter, the rate of the water producing from that filter is very slow. That's why I think there's slow sand filter. In case of rapid, is very fast. So the rate is very fast. And in the statement 2, you can see that the two sand filters do not differ in the respect of effective size of the sand particles. Yes, they will differ. Please check your notes, you will find the exact numbers. Right. So the next one, in the membrane filtration, the degree of selectivity of the membrane largely depends on what? Okay, you are saying that B, but no C. Okay. So the correct answer or answers will be A, B, and C. The membrane charge can determine if this membrane is positively charged and your pollutant is negatively charged, then it can remove. So this will affect the degree of selectivity. Then the porosity depends upon the pores here. If the particles are lesser than the pore size, so it will prevent them from going this way, from here to there, this side, or the treated water side, permit side. And the next one is TDS, concentration of the raw water. Yes, if the concentration is more or the less, that will affect the selectivity of the membrane. The next one is, let the permeabilities of ultrafiltration, that is NF, microfiltration, nanofiltration, NF, then reverse osmosis, BP, UF, PNF, PNF, PRO. Then in general, which of the following is correct? You need to write the correct order for permeability. Okay, so the correct order is, if you are saying the permeability, what will be the correct order? Okay, Nicholas, you are saying B, right? So the correct answer is B. Congratulations, Nicholas. So the correct order is AMF, microfiltration. Then the smaller size is ultrafiltration, this is micro, then UF, then NF, and then RO. So this is the order. Now the source land filters are best suitable for which situation? Okay. So the correct answer is C. Rural community depends on relatively less turbid water source. In that case, we can use slow sand filter. So the population is less in case of rural community, right? So we don't have to provide a lot of water there, and also the water is less turbid. In that case, we can use it. But in case of large urban community, and we are depending upon this, in case of large urban community, we cannot go for this kind of filter because we need high, higher quantity of the water, right? So in case of slow sand filter, the rate of filtration is very less, so it cannot be applied. Then large urban community with high turbid water source, no, if the water source is high turbid, it will clog the sand filter easily. So no. Then this rural community depending on relatively high turbid water, no. The population is less, but in case the turbidity of water is very high. The next one is a numerical question. A membrane module comprised of several tubular membranes has an effective area of 12 meters square. The membrane system is operated in closed flow under a constant flux to yield 1500 liters per hour. The temperature of the water is 20 degrees Celsius. Each tubular membrane is 2 meters long and is operated in an outside-in regime. If the tubes have an outer diameter of 3 centimeter, then the number of tubes in each tubular membrane unit you have to calculate. It's very simple. Don't You don't have to think anything, any idea from your environmental engineering. Better, I would rather say, is very easy geometrical problem. The first one. So we go for the solution. The correct answer is 64. Nothing you need to do here is very easy. That the given effective area was given as 12 meters square. This is the total area, right? So length of each tubular membrane was 2 meter. Diameter is 0.03 meter, right? So this much. This is the thing. So the total area of the membrane module was given as 12 meters square. So I'll write area equals to n number of tubes that required. Suppose so n multiplied by pi dl, and if you put the values of d from here, diameter and L is how much? 2 meter. You have to calculate for n, and area is 12 meters square, right? So if I calculate, I am getting 64 tubes. 64 number of tubes I need. The next one, common data question. If the membrane resistance is 7.15 into 10 to the power 12 meter inverse, then to achieve the required yield, the operation pressure in kilopascal applied across the membrane is how much? And the dynamic viscosity of water is given as 1.0016 into 10 to the power minus 3 Pascal second. So the solution is something like that, and the correct answer is 248 kilopascal. The membrane resistance R naught equals to 7.15 into 10 to the power 12 meter inverse. This is my membrane resistance, and the constant flux, that is JW, we can write as it was 1500 liter per hour, right? 1500 liter per hour. Please convert it first into meter cube per second. Is very easy to convert. 10 multiplied by 10 to the power minus 3 divided by 3600, and I am getting 4.16 into 10 to the power minus 4. Then the JV equals to del P A by mu R naught. So mu is the water viscosity at a specified temperature, and from any book or any datasheet you will find at 20 degrees centigrade it is 1.1016 into 10 to the power minus 3. Same thing it was given in the question. So put the value here, mu value here, and the area was 12 meters square. 12 meters square. Put the value of mu here and also R naught. right? The membrane resistance. If you put all the values, you can calculate what is the del P, right? So you will find del P as 248 kilopascal. The next question is which of the following is not a mechanism for the removal of impurities in depth filtration? So the correct answer is D, solubilization. We are not solubilizing the impurities to remove. If the raw water turbidity is less than 10 NTU, then which of the following treatment trial will be favorable? So the correct answer is B, coagulation, then flocculation, then we'll go for the filtration and disinfection. So if the turbidity is less than 10 NTU, this is the thumb rule. We will now need to go for the sedimentation, right? We will need to go for sedimentation. The next one, if the sand medium has uniformly distributed particle size, then it is best suited for which of the following? Slow sand filter, rapid sand filter, particle size distribution, does not affect the rate of filtration, or none of the above. So the correct answer is B, rapid sand filter. So I already discussed this thing in a previous question. Few questions back, I already discussed in case of uniformity, we prefer a rapid sand filter, but in case of non-uniformity, that is slow sand filter, right? So this is as simple as that. So the next one is you need to check this figure, this graph. So the x-axis is time of filter run, and the y-axis is effluent turbidity NTU in NTU unit. You can see how with time of filter running, the effluent turbidity is changing. So the question is, after the duration of 90 hours, which of the following operation would you suggest in a deep filter? Sorry. Um, change the filter media, backwashing, filtration should be continued, scraping the top layer. But you have to be very sure about this thing that it's a depth filter. So the correct answer is backwashing. The change of the filter media, no, not it should not be done. And the filtration should be continued. No, you need to change. Otherwise, what will happen? That the effluent turbidity will increase in the water, right? It's increasing. You can see it's increasing. After some time, it will reach a certain amount. Then the scraping of the top layer, no, because in case of rapid sand filter only, we will scrap the top layer, but everywhere. But in case of in case of rapid sand filter, mostly the top layer is working, right? Where the straining, adsorption, and the sedimentation is happening. But in case of depth filter, in every portion of the filter, it's acting for the filtration, right? It is doing the job of the filter. So you have to clean all the sand particles everywhere, not only the top surface. So scraping of the top surface is not a base job for this depth filter. The only option is filtration. Only option is the backwashing. Pardon, I'm erasing this. So I have only one option, that is backwashing. So if you push the water from the down below, it will wash all the impurities present at various depth of this filter. This is again a common data question, 6 and 7. A sand filter is to be provided in a water treatment plant that caters to a population of 1.2 lakh. The average water demand is 140 liters per capita per day, and the rate of filtration is 16 meter cube per meter square per hour. The design allows the filtered water for the storage to meet the backwashing requirements, and the filtered bed is required to expand by 0.4 meter. The required backwash velocity is what? In meter per second. You have some given data. The first one is the porosity of unexpanded bed, that is 0.5. Then the coefficient of drag, that is 5.02. Kinematic viscosity 1.004 into 10 to the power minus 6 meter per second. The depth of the filter media, that is 1 meter. The depth, mean diameter of filter media particles, that is 0.6 mm. Specific gravity of the filter media 2.5. Density of the water 1000 kg per meter cube. Try to solve this as quickly as possible. So I'll go for the answer, that is 0.01 to 0.014 meter per second, and I'll go for the next question, then I'll show you how to solve, because these two are connected questions. So the next one, head loss in the filter before backwashing. In meter you have to calculate. Okay. The answer will be 0.73 to 0.77 meter, depending upon your calculation. So the first one is this one is the given data. The specific gravity of the filter media was 2.5. So from there, we need to calculate what is my density, rho s, of the filter media, sand, and I can multiply with 1000 into 2.5. So all of you know that is the specific. This is density of the sand and density of water. You will get the specific gravity of sand, right? So if you multiply with the density of water, we will get the density of filter media. So density of filter media is 2500 kg per meter cube, and head loss, we know this formula, head loss equals to rho s minus rho w multiplied by 1 minus the porosity into d divided by rho w, right? So my rho s, or the density of my filter media, is 2500 minus 1000, is the water density, 1 minus 0.5 because it was given the porosity of unexpanded bed, right? We need to calculate the head loss for unexpanded bed. So I'm using this porosity 0.5 multiplied by the depth, that is 1 meter, and divided by 1000, the rho w. I'm getting 0.75 meter as head loss. The next one is your backwashing velocity. So the settling velocity according to Stokes law, Vs equals to root of 4 s g minus 1, that is the specific gravity, multiplied by g into d g, or there you can see this is the diameter. Basically, this is nothing but the diameter divided by 3 into cd, that's coefficient. So 4 multiplied by 2 by 2.5. 2.5 was the specific gravity of this media. Then what is the specific 1 minus, sorry, minus 1 into g value 9.81 into 0.6 into 10 to the minus 3. This is my diameter of the sand particle. 3 into how much it was there. That CD was given as, is there any value for CD? Yes. The coefficient of drag is 5.02, right? So I'm writing this 5.02. This 5.02, right? 3 into 5.02 coefficient of drag. If you calculate the settling velocity of the particles, I'm getting a 0.048 meter per second. Why this settling velocity is required? Because after this backwashing, these particles which are at the floated condition or the expanded condition, they should settle down, right? So I'm taking care of the settling velocity here, and from this settling velocity, I will calculate the Reynolds number, right? So dg is this is my diameter multiplied by Vs divided by my viscosity. This is the viscosity. Viscosity was given as 1.004 into 10 to the power minus 6 meter per second. This is my kinetic viscosity. So it is dg. This is the diameter of the particle multiplied by the settling velocity. I got Vs as 0.048 meter per second divided by the viscosity. If you calculate, you will get as 28.68 the Reynolds number for the particle. Now the porosity of the expanded bed, you can write this formula. This is very easy. 1 minus epsilon E, this is the porosity of the expanded bed, multiplied by dE expanded depth, equals to 1 minus epsilon, that is the unexpanded bed that it was in the normal condition. What is the porosity and what is the depth? So in case of unexpansion, it was 1 meter only. In case of expansion, expansion should be 0.4 meter, right? So the total depth will be 1.4 meter, 1 plus 0.4. And epsilon in case of unexpanded bed, it was 0.5. So if you put all the values here in this equation, you will get epsilon E, that the porosity of the expanded bed, as 0.642. So here you can see that the porosity is increasing, right? For expansion, that's very sure because the bed is expanding, so the porosity will increase. Then this epsilon E equals to Vv, this is back passing velocity divided by Vs, settling velocity. to the power 0.2247 Re to the power 0.1. Empirical formula I am using. So from this empirical formula, you can calculate what is the Vp. Just put all the values, epsilon E value here, and you know what is the Reynolds number, and also the Vs, the settling velocity. So Reynolds number is 28.68 and Vs settling velocity is 0.048. Put all the values, you can calculate what is Vp, that is 0.012 meter per second. This is my backwards velocity. The next one, the separation limit for a membrane is determined by the lowest of what you fill that portion that can be separated. Okay. The correct answer is molecular weight. Based on this molecular weight, we can say what is the limit of the separation of a particular membrane. For in case of nanofiltration, in case of ANF, in case of RO. So depending upon this molecular weight, we can divide. The degree of selectivity of membrane is largely dependent on. So the correct answer is A and B. I already discussed similar question in today's session. So the membrane charge is membrane charge. Depending upon your pollutants, it might be negatively charged. Your membrane might be positively charged. So it will repulse all the pollutants, right? So there will be some repulsive force, and the porosity of the membrane is very easily understandable. That if the porosity is bigger, then it will pass. But if the porosity is lesser, then the pollutants will not pass through the membrane. So dialysis in our kidney is what? Which kind of separation process? So this is as similar as our membrane technology. So it is concentration driven separation process. It is not thermal driven separation process in our body. Neither the pressure is there, which is actually forcing the water to pass. Neither there is some temperature difference, but it's a concentration driven separation process. Thank you everyone for joining today's session. I hope you enjoyed and learned many new things. So we'll meet on the next Tuesday at the same time. Thank you for watching.